Welcome to the CopperSpice YouTube channel, and thanks for joining us. In this video, we are going to introduce futures and promises and talk about why they are of value. Futures and promises. We are going to begin by providing a quick overview of where the concepts of futures and promises originated from and where they can be used. Then we want to explain a bit about each component and show a few examples of how these classes can be used to solve a few particular problems. We will also look at async and how it fits into the future and promise system.
Futures and promises are an abstraction originally developed in functional programming languages to handle concurrency. These concepts allow a program to pass values between threads without using any of the typical synchronization mechanisms used when sharing data between threads, like mutexes. One of the challenges with using futures and promises is mostly centered around the terminology. Various terms have been used by different researchers, developers, and computer languages to mean very similar things. It can be challenging to figure out which definition is being used in a given context, and in fact some have said the class names for futures and promises should have been reversed. In this talk, we will be discussing all these terms as they pertain to C++ specifically. Futures and promises are useful when you have some operation or set of operations which produce a result, could take a significant amount of time, or may not need to happen in any particular order. A good example of when you might use a future and a promise to improve performance is when you're reading or writing data, like opening a file in an editor. Ideally, it would be good to allow the user to continue interacting with the program after the first portion of the file has been loaded. The remainder of the file could then be loaded in the background. A common way to implement this is by using a future. Or you may have a system which is making a call to a web service or using a raw TCP socket, and you don't want to wait for this operation to complete before moving on to another task. Another example is when doing database queries or distributed systems which often have long-running tasks. This is only a short list of places where futures and promises can be utilized. It's worth noting that these constructs are not limited to a fully multi-threaded application. In the late 70s, the term promise was first introduced, and then a year later the idea of future was introduced. Over the next 20 years, they were implemented in a few lesser-known computer languages. These constructs were considered mostly theoretical at the time. They were not originally developed to solve the modern-day problems we have with networks, web servers, and distributed systems. 30 to 40 years later, we're finally realizing the value of this technology. Futures and promises were not widely known until early 2002, when Python introduced the notion of what they called deferred objects in a library called Twisted. In 2007, the Dojo deferred library added these concepts to JavaScript. The Boost library introduced one of the first thread libraries for C++ in 2001. It wasn't until 2009 that the Boost thread library added functionality to support futures and promises. With the release of C++ 11, futures and promises became part of the standard library. There have been several new proposals to expand the functionality of futures and promises in the C++ standard, and these are available as experimental in some compilers. It is expected that C++ 20 will contain most of these enhancements.
When you're looking at a computer language or browsing through code samples on Stack Overflow, you need to be very careful. Not every computer language has both constructs, namely futures and promises, and the definitions and implementations may be different. We ran into this when we were looking at some sample code, and it was using a promise. The code seemed unusual or even incorrect. Then we realized this was not C++ code, it was actually JavaScript. If you are using futures and promises in a language other than C++, these constructs may not be in the core language or standard library. In most all cases, futures and promises will be supported in various third-party libraries.
In C++, a future is an instance of a templated class. This object is read-only. Its purpose is to encapsulate a value that may not be available yet, but will be provided at some point. The template parameter for the future template indicates the type of data the future will hold. The primary way you work with a future object is to call the get method. Calling get will retrieve the data stored in the future. If the future is not yet ready, meaning the data has not been provided, the call to get will block. If for some reason an error occurred while computing the value, the get method will throw an exception. The promise instance is also an object of a templated class. Just as with a future, the template parameter indicates the data type of the stored value. The T for the promise and the T for the future must match. This may seem a bit odd, but if you create or instantiate your own future object, it will always be invalid and it cannot be used for anything. There is no way to make this future valid. The only public constructor for a future creates an invalid empty future. To create a usable future, you first create a promise. When the promise is instantiated, it automatically creates an invalid but usable future object, which you can then extract from the promise object. This future will become valid when the promise fills in the data. This is called fulfilling a promise. As a recap, the purpose of the promise object is to guarantee that some function will compute some value and make it available in the corresponding future object.
So how does all this work? A typical usage involves first creating a promise object. From the promise object, you extract the future and hold on to it. Then you move the promise to another thread or function. Once the function has finished, it is responsible for setting the value in the promise, and the future becomes available. At any point, the main thread can call the get method of the future object to wait for the data in the future to be available. If the function has already finished, the call to get will return immediately. If it is not available, the call to get will wait until the future is finished. So what happens if the function fails? If the promise contains an exception, when the main thread calls the get method, the exception in the promise will be thrown. There are two ways the promise might contain an exception. If the function encounters an exception, instead of actually throwing, it should place the exception object in the promise. This allows the exception to be thrown later when get is called and not in the function itself. It would be a very bad practice to throw an exception in a thread since it is unclear who should catch it. According to the C++ standard, throwing an exception in a thread calls std terminate. If the function does not set a specific exception in the promise, then the promise will go out of scope without being fulfilled. When this occurs, the promise automatically sets a generic exception in the future. This is called a broken promise exception. This is accurate since the promise was not fulfilled, and the function has therefore broken its promise to compute a value. The problem with relying on the broken promise exception to be set is that it actually does not indicate why the promise was broken, and it's not a very meaningful error.
Here is a simple example that uses a future to store a computed value generated as a result of some function. The main function creates a promise and extracts the corresponding future. A new thread is then started to run the doWork function, and the promise object is moved into the thread. The main thread then calls get and prints the result. The threads are joined to complete the process. Notice the T in stdPromise and stdFuture are both int. If you were to change the t for stdfuture to a double, you would get a compile error saying something like conversion from future int to future double requested. The doWork function will run at some point after the thread is started and before the call to get returns. Since the main thread cannot continue until the value is available, it waits. If the main thread runs first, it may be blocked until doWork has completed. The reason the promise and future are separate objects is to encapsulate the two different sets of functionality. The promise is used by the function which is responsible for computing a value in order to store the return value or exception in the corresponding future. The future is used by the caller to retrieve the information which was computed. This is why the get method exists in only the future, and the setValue method exists in only the promise. The future promise mechanism works very well when you have different threads working on different tasks, and the results need to be combined together by a main thread. In this use case, the fact that get will block is not consequential. In fact, it's expected. We have some larger task which can be broken down into 5 different parts, and each part can run independently. The idea is to start one thread for each of these tasks to speed up processing. In this use case, we start 5 threads and pass a unique promise to each one. The main thread simply gets the values from all the futures in turn. As soon as all 5 tasks are complete, then all 5 calls to get will be unblocked and the values will all be available to the main thread. One of the problems with STDfuture is that it offers no way of notifying anyone when it's ready. In some cases, like the use case we covered in the previous example, this is not an issue. However, since the get method can block, this may need to be part of your design considerations. What you can do is call the waitFor method with this awkward argument specifying an immediate timeout. The return value of the waitFor method will tell you if the future is ready. This gives you a way to ask, if I do call get, will I block? However, one of the missing features which would be very valuable is the ability to chain futures together. The idea would be that when a future is ready, another process is started and a new future is passed to some function, and another value is computed. Unfortunately, this technology is not available in any current version of the C++ standard library. The Boost Thread library added a method called then, which can be passed a lambda or a function. When the future becomes valid, the lambda or function will be invoked. This is sort of like a signal slot connection. The lambda or function is passed the return value which was just placed in the future. This means you're not blocked by calling the get method on the future, and in fact once the future becomes valid, data is automatically passed to the next function in the chain. Developers have been asking the Standards Committee to add a similar method to the standard library for several years. There was hope this would be part of C++ 17, however it was not approved. For various reasons, many of which are quite compelling, this method, along with several other new ideas, were moved into the SG1 concurrency technical specification. There is some belief a change to futures may be part of the C++ 20 standard. One of the complexities they are heavily considering is how to determine which thread should invoke the various parts of the chain. Should then be passed a reference to a new thread? How do you pass the ID of the thread where the chained future will be run? What if you want the chained future to run on any one of several threads in a thread pool? There are lots of questions with few clear answers right now in this area of the standard.
Since futures and promises can be somewhat cumbersome to use, the standard library provides a function called STDAsync, which encapsulates a portion of the complexity of setting up a promise and a future. Async provides the abstraction of calling a regular function in another thread. The return value of the thread will automatically be returned in the future. Internally, async manages the promise and calls the setValue method in the promise when the function returns. If there is a failure, async will call setException to indicate a problem. Basically, STDAsync provides a higher level mechanism to call an ordinary function in another thread and retrieve the value when it's ready. It is valuable to note the function which is called does not have to handle futures or promises in any way. It can be a normal function which takes parameters and returns value. This means async allows you to call existing functions in a separate thread without modifying the original function. Here is a generic example showing how STDAsync would be used. The calls to get are still blocking. The only guarantee is that both computations are complete and their corresponding futures are ready before the addition of the two values can happen. In a real-world application, you may need to handle the case where one of the get methods might throw an exception. If this happens, the return expression will not be evaluated, and instead the exception will be propagated to the caller of the compute and sum function.
The idea of futures and promises are relatively new to C++, but they have been around in functional programming in other languages for many years. What was added in C++11 was a good start, and there are very talented people on the Standards Committee who are looking to advance this technology with the addition of methods like then, or when all, and when any in C++20. For now, we have the beginning of futures, promises, and async. Once you are aware of the limitations of the current standard, there is a great deal of improvement you can make to your application design and leverage asynchronous computations. One of the huge advantages of using futures is to facilitate the ability to return a value from a thread. This allows functions in multi-threaded code to be structured more like normal procedural code. For more information about the CopperSpice project and the libraries we have developed, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, please feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back in 2 weeks for our next video.